Welcome to the UNV certification program. The topic of this video is optic fundamentals. After you have learned this course, you will get to know the basics of optics, including color temperature, white balance, exposure, shutter, illumination, saturation, and contrast. And have a further understanding of optics professional terms, including WDR, spectrum, ICR cut, digital noise reduction, and defog. Let's start with optics basic knowledge. First, white balance. White balance is used to adjust colors to match the color of the light source, so that white objects can appear white. Subjects may be lit by a number of different light sources, including sunlight, incandescent bulbs, and fluorescent lighting, and all the different light sources emit light of different colors. The image sensor in a digital camera will reproduce these color differences just as they are. Therefore, without additional processing, the color of the photograph would appear to change according to the different color temperatures of the light source. So, here is another relative definition: color temperature, which is the most common indicator of the spectral quality of a light source. Color temperature light source is characterized by the energy distribution. The lower the color temperature, the more the red radiation, usually called warm light. Color temperature increases, the proportion of blue radiation increases, usually called cool light. The same object under different color temperatures appears in different colors. That is, object under a low color temperature light source tends to be red, whereas a high color temperature is relatively blue. And here is a spectrum below. We can more intuitively see the color temperature and energy distribution. Here's a chart that gives you a few different light sources and their typical range of Kelvin measurements. A neutral color temperature measures between 5200 to 6000 Kelvin, and most external flash units come set from the factory in that range, which means they are basically trying to imitate sunlight. An incandescent light bulb has a color temperature of around 3000 Kelvin, while shade has a color temperature of around 8000 Kelvin. Next, let's see the shutter. Shutter includes mechanical shutter and digital shutter. Mechanical has a physical door in front of the lens. When you press the shutter button, a mirror flips up, allowing light to pass in the camera instead of the viewfinder. Once the mirror is flipped upwards, a small door will move from top to bottom, exposing the sensor beneath. After that, another door will fall, covering up the entire sensor. After the second door closes, the mirror will fall back into place. The door will then reset to original position underneath. The longer the shutter is open, the more light will enter the camera. Digital shutter adopts the principle that CCD or CMOS doesn't work without power supply, so it can power on and off to control the pixel of sensor. Therefore, there are no physical moving parts of opening and closing of a shutter. Digital shutter is generally from 1 second to 1 out of 100,000 seconds, which can be shorter than mechanical shutter, and has a faster shutter speed. Shutter speed is the length of time the camera's shutter is open, exposing light to the camera sensor. Essentially, it's how long your camera spends taking a photo, and measured in fractions of a second. For example, speed of 1/50th means allows in light for 1/50th of 1 second. And shutter speed is responsible for two particular things: changing the brightness of photo and creating dramatic effects by either freezing action or blurring motion. If you use an especially fast shutter speed, you can eliminate motion even from fast-moving objects, like birds in flight or cars driving past. If you use a fast shutter speed while taking pictures of water, each droplet will hang in the air completely sharp, which might not even be visible to our own eyes. All of the above is achieved by simply controlling the shutter speed. In summary, quick shutter speeds freeze action, while long ones create an effect of motion when you photograph moving objects. So, here comes a question. When at night, how can we capture the license plate of a fast-moving car? Should we use a fast shutter speed to avoid motion blur? As we mentioned before, shutter speed can be a vital tool to capture a photo of the proper brightness as well. The smaller the shutter speed, the longer the frame is exposed to light, resulting in a brighter image. In other words, the shutter controls how long the frame is exposed to light. The faster the shutter speed, the less light reaches the frame, resulting in a darker image. On a sunny day, you may need to use a fast shutter speed so that your photo isn't overexposed. Or, if it is dark out, a long shutter speed may be necessary to avoid an extremely dark photo, which, in turn, could require a tripod due to motion blur from hand-holding the camera. This is the main reason to adjust shutter speed, to make sure your photos are the proper brightness. However, shutter speed is not the only variable that affects the brightness of an image. There are also apertures and ISO, along with the actual brightness of the scene. While shutter speed controls exposure by adjusting the time of incoming light, aperture controls exposure, which we will introduce later on, by adjusting the amount of incoming light per unit of time. So, we have some flexibility when we're deciding on a shutter speed, but still need to pick other settings carefully. Then let's go back to the question. While capturing license plates of fast-moving cars in the dark, a fast shutter speed can effectively avoid motion blur of the image, along with a large aperture to ensure brightness. Then, here comes the exposure. Exposure is the amount of light per unit area reaching a frame of photographic film or the surface of an electronic image sensor, determined by shutter speed, lens f-number, and scene luminance. Overexposure leads to overexposed highlights and faded-looking images. Underexposed images are dark and hard to see. Pictures below show different exposure of the same image. The larger the exposure, the brighter the image. The next related parameter is contrast, which refers to the measurement of different brightness levels between the brightest white and the darkest black areas of an image. The larger the difference range, the greater the contrast, and the smaller the difference range, the smaller the contrast. Except for the above parameters, illumination creates a significant effect on images. It refers to the degree to which an object is illuminated, known as light intensity. It is expressed by the luminous flux received per unit area. The chart below shows the illumination of the common natural light in different weathers. Saturation describes the intensity of color, also known as the purity of color, which is determined by the ratio of chromatic and achromatic components in the color. A grayscale or black and white photo has no color saturation, while a full-color photo of a field of sunlit wildflowers might be extremely saturated. Which means, the larger the color component, the greater the saturation. The larger the achromatic component, the smaller the saturation. Now let's move on to optics professional terms. We will start with WDR. WDR is short for wide dynamic range. First, let's see what is dynamic range. In the camera field, dynamic range refers to the camera's ability to adapt to the light reflection of the scene in the shooting scene, specifically referring to the range of the contrast of brightness and color temperature. In other words, it is the ratio of the brightest and darkest points of the image. And wide dynamic range uses one sensor with each point above exposes twice in a single time. A long exposure and a short exposure, so there are two data outputs for each point, called dual output exposure. Send the obtained long exposure and short exposure signals to DSP to calculate and mix, allowing us clearly see the darkest and brightest part of the image. DWDR, short for Digital Wide Dynamic Range, is the easiest technology to implement WDR technology, which is to improve the contrast of local areas through the image post-processing algorithm, generally realized by the camera ISP module. DWDR is to enhance the weak grayscale differences through image processing algorithms to allow it to be recognized by human eyes. The line here indicates the bright part and dark part of an image, which shows that DWDR basically dims the brightness and brightens the darkness. Next is spectrum. The types of electromagnetic radiation are broadly classified into the following classes: gamma radiation, X-ray radiation, ultraviolet radiation, visible light, infrared radiation, microwave radiation, and radio waves. This classification goes in the increasing order of wavelength, which is characteristic of the type of radiation. Through the spectrum, we can see that there are no precisely defined boundaries between the bands of the electromagnetic. The infrared part of the electromagnetic spectrum covers the range from roughly 1 mm to 750 nanometers. It can be divided into three parts: far infrared, mid-infrared, and near-infrared. An infrared light can help us get the black and white image at night. Electromagnetic radiation with a wavelength between 380 nanometers and 760 nanometers is detected by the human eyes and perceived as visible light, which basically can be divided into the following 7 colors. And we can see their wavelength, frequency, and photon energy here. Other wavelengths, especially near-infrared, which is longer than 760 nanometers, and ultraviolet, which is shorter than 380 nanometers, are also sometimes referred to as light, especially when the visibility to humans is not relevant. White light is a combination of lights of different wavelengths in the visible spectrum. Passing white light through a prism splits it up into the several colors of light observed in the visible spectrum between 400 nanometers and 780 nanometers. And the wavelength of ultraviolet rays is shorter than the violet end of the visible spectrum but longer than the X-ray. With different wavelengths of light, an infrared cut filter will filter the target light, achieving the best effect of the image in day and night mode respectively, and an anti-reflection filter will enhance visible light at night. While the camera receives both visible light and infrared light, the image will appear color of violet due to the effect of infrared wave. Therefore, putting an infrared filter can greatly solve the problem. In the daytime, close the filter, only the visible light can go into the camera, and we can get a colorful image. When it's dark outside, open the filter to let the infrared light in, so we can receive the image information, although it's black and white image. Since surveillance cameras are often installed outside and are expected to stand the test of 24 hours 7 days operation, they are frequently exposed to strong light, rain, snow, and fog. These environmental conditions have a great influence on the image quality of the surveillance camera, especially the fog. The aerosol particle containing moisture and fumes in the fog will lower the contrast ratio and cause the degradation of the image quality, so that the details of the scene can't be seen clearly. Therefore, defog technology is one of the imperative technologies for outdoor surveillance. Since near-infrared light is less affected by aerosols, it can penetrate a certain concentration of haze dust, achieving the defog effect. The 3-filter scheme is used to let the near-infrared light into the sensor imaging. However, only let the near-infrared light in will affect the brightness of the picture. Defog technology needs the camera to switch to black and white mode. One of the liabilities of this physical is its high cost. Advancements in the development of digital technology bring about defog image processing technology. Digital defog adjusts the distribution of the information captured by the image sensor and enhances the color and details of the surveillance target to decrease the information loss during subsequent processing, such as ISP and encoding compression. Compared to optical defog, digital defog costs less and can create colorful images. However, it will miss information in the severe fog environment. Once the concentration of fog in the environment changes, the effect of digital defog penetration will be uncontrollable. Except for fog, the signal-to-noise ratio can cause a vague image. Signal-to-noise performance directly determines the camera's output image quality under low light conditions. Therefore, we use digital noise reduction technology to suppress the noise in images to obtain a better effect. However, it is also should be noted that excessive noise reduction can distort the picture and cause blurring or smearing. Recently, we used 2D and 3D to achieve digital noise reduction. 2D DNR does noise reduction on a single image, and does it on each pixel with the surrounding pixels, to make the average noise reduction. However, it will cause the picture blur, especially the edge of the object. 3D DNR adds time domain processing. The difference from 2D DNR is that it considers the time domain relationship between frames and frames. 3D overlay two neighbor frames to find out the same noise point, then reduce the gain of them to reduce the noise. After this course, you must know the basics of optics, including color temperature, white balance, exposure, shutter, illumination, saturation, and contrast, and have a further understanding of optics professional terms, including WDR, spectrum, ICR cut, digital noise reduction, and defog. That's all for optic fundamentals. Thanks for watching. See you next time.